Hello, we're Team 98, Tissue Therm, sponsored by Dr. Slepian and Regenesis Biomedical. My team and I have been working long and hard to devise a product to analyze the effects of a novel therapy on organic tissues. I hope you enjoy our video.
Thanks for seeing me on such short notice. Ever since my surgery, I've had the worst chronic pain.
Well, fortunately, there's a new therapeutic device that utilizes pulse electromagnetic fields to reduce pain and speed up recovery.
Oh, can you tell me more about it?
Of course, while the system has been proven to alleviate pain, the working mechanism has not yet been fully researched. I have a specialist here to tell you more about it.
Hi. As the doctor mentioned, I'm working with Regenesis to look into more what this therapy does and the thermal effect of the study. I can tell you more about it. As I mentioned earlier, my team is looking into the thermal effects of the pulse electromagnetic field therapy, and we built a test bed that's able to sense temperature, magnetic field, and electric field spatially within a tissue sample and display the results. And with these results, we can further research being done on tissue regeneration using pulse electromagnetic field therapy. And my teammate here is going to tell you more about our test bed and what we built.
This is an overview of our basic system design. Our system sits on top of a PEMF pad. Our sample tank houses the tissue sample. Temperature sensors are inserted in through the top of our sample at varying depths. H field and E field sensors are inserted through the sides of our sample tank. Next steps are implementing an environmental control system which uses heat exchange to keep the inside of our sample tank at body temperature. For this design, we have found that the temperature sensors are within 4% accuracy of a gold standard. Our electric field and magnetic field sensors are comparable in readings, and the sample tank can hold various types of tissue specimens and materials. In addition, our system operates consistently during the 30-minute PEMF duration. Our design follows standards for electrical safety, sanitization, and ethical sourcing of animal products. I'm going to hand it off to Alexis to tell us more about the sensors we chose.
Hello. So, when we were designing on temperature sensors for our setup, we needed to have a sensor that was resistant to EMF, could get highly accurate readings, was capable of updating quickly, could interface with the computer, and was waterproof. We initially considered thermistors, as they are EMF resistant and cheap and accurate. However, they are not in pro form and are not waterproof and are not capable to interface with the computer. We then considered thermocouples, which are easy to interface with the computer. However, they are prone to EMF distortion. We ended up picking resistance temperature devices, or RTDs for short. These PT100 RTDs are capable of meeting all of the requirements that we need to, albeit they are slightly more expensive. To ensure sufficiently strong pulse electromagnetic field is reaching the tissue sample, we're using Beehive 100A magnetic field sensors and Beehive 100D electric field sensors. These sensors interface with an off-the-shelf oscilloscope, such as a Sigma SES 1104XE. We are currently using 4 sensors in our system, the oscilloscope recording the data from all 4 and plotting it against real time. We're using 2 100A magnetic field sensors and 2 100D electric field sensors.
And now I'll take a moment to walk you through how our design has evolved throughout this project.
The design of this project has changed a number of times throughout its development. The majority of these changes have been to ensure that the various sensors are in optimal positions to gather the data that we need. The sample tank's walls have shortened to get the probes closer to the surface of the Provamp pad. The tubes atop the sensor holster have changed in height to achieve a better distribution of collection points. In addition, the sensor holster sits sunken in its guide rails to ensure that the probes are consistently in the same spot for each run. We have put holes in the tank walls to allow the EMF probes to be parallel with the PEMF emitter. Finally, there are guides for the vinyl tubing along the inside of the tank to make sure that they do not interfere with the sample.
Alright, next we are going to take you through our user interface and show how an operator would run this program with ease.
Our first step is to inform the interface about our sample. We have two different options for the sample size: square rectangle, such as a molded biomimetic gel, or circle ellipsoid, such as a raw chicken breast. We can also input the sample's length, width, and height in millimeters. There are automatic inputs oriented that represent an average expected sample size, but these can be adjusted as necessary. Then we can begin the data readings by pressing this button. This thermal data will be stored into a CSV file and saved to the folder for future use. Next is to decide the thermal output options you want to display. We can first discuss the 3D thermal map. Currently, there's an arbitrary temperature dataset included to show the real-time color changing capabilities. We can see that the shape of the sample aligns with our input, the 12 different temperature probe points, and the time displayed in the top left. There is also an option to place labels of the temperature probes onto the graph as defined in the user's manual. This 3D animation is automatically saved to the folder with its name, including the date and time it was recorded. The next display is our temperature table, which shows the temperature values real time and is aligned with our 3D thermal display. While we're here, I will also show you what a circle ellipsoid sample looks like. With this, we can also see that if you try to generate these graphs again, a warning will pop up to ensure this action. Our next output options are for the electric and magnetic field sensors. This data is manually exported from an oscilloscope and uploaded to the interface. First, you can see that if we try to generate a graph without an uploaded file, it will give you an error. So let's go ahead and upload a data file. Next, the user can define how the sensors are oriented on the oscilloscope channels and select a graph to generate. These graphs are generated separately because the relativity of their values are very different, and this allows us to get a better read of the data. Both of these graphs are also automatically saved to the data file.
I will now be discussing the different subsystems that make up this final product.
When looking into MVP1, we integrated several components to ensure that the RTDs were getting correct values. The figure to the left illustrates the Arduino and software system. The figure on the right illustrates the temperature reading on the computer that come from a single RTD, which has been placed in the sample that is on top of the EMF pad. Testing one RTD at a time allowed us to verify that each RTD was reading accurate temperature values. Moving forward to MVP2, we verified that the electric and magnetic field sensors were working simultaneously with 4 RTDs. We interfaced with the electric and magnetic field sensors using an oscilloscope, as seen in the figure to the left. The figure on the right shows how the magnetic field sensors are placed parallel to the EMF pad to obtain better readings from the sample. The oscilloscope then takes these readings, which gives us the EMF strength as well as H-field values, later used in the GUI. In our final MVP3, we tested that all 12 RTDs were working simultaneously to get temperature readings, while the E-field and H-field sensor also got EMF strength readings. The data from these sensors are then displayed on the GUI. A complete 30-minute session was ran to ensure everything was working and that we could accurately display the data obtained from the sensors for the standard duration of the therapy session.
This project did not come without its challenges. Initially, we had connectivity issues with the RTDs, so to mitigate this, we directly soldered the sensors to their amplifiers. We also had complications with the EMF interfering with the computer, so we now ensure that they have proper spacing between them. An important consideration of this project has been making sure that the various components operate cohesively. We believe that this technology has the potential to revolutionize pain reduction, as it is both easy to use and infinitely reusable. Our goal is to aid in the research of the safety and understanding of this device's working mechanisms. This has been Team 98 Tissue Therm. Thank you for watching.